Okay, so let us go on to the next section here. Let the video do its thing. It's going to switch over to the next video. There we go. All right, so next up we have integrals of trigonometric functions. My apologies, the dishwasher just come on because it's that time of night. I'm going to turn the mic down just a bit, if I can. Mic level, mic. There we go, just a bit down. Hopefully you'll just hear me mostly. So integrals of trigonometric functions, I already did some of these in the homework for you guys, so you kind of already have seen the trick. But there's a nice example. Basically, to just work backwards from, an integral that you're given in terms of a rational function and in terms of sines and cosines, and look at it as an integral around the unit circle, right? So this one, integral d theta 5 plus 4 sine theta. So you're the drill at this point. We do what? We do z equals to e to the I theta. So then dz is I e to the I theta d theta, which is of course iz d theta. So d theta actually is dz over iz. And on the flip side of things, we can write cosine and sine, right, in terms of the usual. I'll write it over here. Right, we've got cosine theta is 1/2 e to the I theta plus e to the minus I theta, and sine theta is 1/2, 1/2i rather, e to the I theta minus e to the minus I theta. And of course that, if we re-express it in terms of z, that's 1/2 z plus 1/z, and sine theta is 1/2i z minus 1/z. All right, so with these substitutions in mind, of course, we can convert an integral from 0 to 2 pi to an integral around the unit circle of a rational function in z, which is lovely because we can calculate these with the residue theorem pretty nicely. So that's what we do. Here's dz over iz, and I traded my sine theta for I over 2. So I put, you can bring the I into the numerator by making it minus. So minus I over 2 z minus 1/z. And then I just do algebra. We get to this. I show you you can factor that like so. So you've got zeros at minus I over 2 and 2i. And let's see here. So if you look at minus I over 2 and 2i, and you think about the context here, right? Well, context says only one of those matters because we're in the unit circle, right? And so for the unit circle, here, minus I over 2 is maybe here, right? But minus 2i would be down here somewhere, right? So this point right here on the unit circle would be minus I. This point up here would be I. This point over here would be 1. This point over here would be minus 1 for our unit circle, right? But we only care about these singularities, really. And only one of them's inside the unit circle. So by residue theorem, the integral is 2 pi I times the residue at the singularity inside the circle, which in particular is this, which we use rule 4 on to dispatch it with ease. 4z plus 5i, evaluate it minus I over 2, bam, there's your integral. So, this next example, it's more beastly. So, tell you what, maybe I'll save that example for class. Oh no, I should do it now. I'll do it now. No, I'm going to save for class. Save for class. Either save for class or just let you read it. I wanted to spend the rest of the time on some of my old materials. I will just mention the principal values thing we'll come back to again, but it's over here. Section 10.6, I defined quote-unquote principal value, which is just a fussy point about the difference between an improper, doubly infinite improper integral and this principal value may exist even though the double integral, the improper integral doesn't exist. All right, so let's take a tour through some materials. All right. So this is an old test 2. I think it's kind of fun to go through this for a few minutes. So, because it's more or less where we are in the course at the moment. Let me pull this off here. All right. No. Yep. Nope. Yeah. All right, there we go. I'll get it eventually, guys. So here we go. Problem 1, find the Laurent series for this guy. So what do? I just plug in 1 over z squared into the Maclaurin series for a sine and multiply z squared through and simplify. That's it. Doesn't have to be hard. Problem 2, find the residue of f of z at 1 plus I for log z over z minus 1 minus I squared. So that's a double pole because log z is not singular there. And so we can use the rule 2 basically, which I do here. And there it is. Piece of cake. Problem 3 is exercise on multiplying series. I did that in class already for you guys, actually. That's my stupid, oh look, it's the laws of exponential when you multiply an example. Yay! All right, moving on. Problem 4. Derive Laurent series expansion for f of z equals to 1 over z times 1 plus z squared on annuli centered about 0. So basically, if z is less than 1, then I can geometric series this thing like so and get that. And then I've got 1 over z is actually 1 over z times that. And then, again, the context here, 1 over z, less than 1. So I've got, the 0 is a singular point, right? So in the middle, there's your 0. But this formula, right, holds in there. That's the Laurent expansion in here, up to modulus is equal to 1. Now, if modulus z is bigger than 1, then, like you're out here and stuff, right? Out here, modulus of z greater than 1. And in that case, we go to the calculation down here. So if modulus of z is greater than 1, and I've showed you guys this trick already, but let's see, it doesn't hurt to see it again. We just, factor out 1 over z squared, and that makes this z squared become a 1, and that become a 1 over z squared, which is lovely because that has modulus less than 1 in this case. And then I can geometric series this thing, leave the 1 over z squared out front, and then, simplify, and I get that. There you go. That's the Laurent expansion on the outer annulus. It goes all the way out to infinity. So that's problem 4. Problem 5. Calculate the integral over the circle of radius 2, positively oriented, in other words counterclockwise, of the tangent. So tangent sine over cosine. Cosine is 0 for plus or minus pi over 2, both of which are inside that circle of radius 2, because pi over 2 is 1.57, blah, blah, blah. We know this, right? We know this. Or we'll learn it. Or we'll get our calculator and find out. Well, yeah, I don't know. I can't fix that if you don't know about that. What you don't know about pre-calculus can hurt you in this class. It's true. I don't deny it. So plus or minus pi over 2 are relevant. And the residue of this guy at plus or minus pi over 2 is given to us by rule, I want to say 3. Evaluate the numerator function at the singularity and differentiate the denominator and then plug in the singular points. And in both cases, we get -1. And as such, the residue theorem gives us the integral of tangent z dz over the circle radius 2 is 2 pi I times the sum of these residues, which is both -1, so we get a -2 times 2 is -4i, 4 pi I. There you go. Oh man, I love this residue theorem. This residue theorem, it's just nice. All right, so well, let's see what's up next here. Part B, calculate the integral of cosh pi z over z squared, z times z squared plus 1. So z, and again, it's the same circle of radius 2. And so there's 0 and plus or minus I. There's three singularities inside the circle radius 2. And so what I do, I calculate the residue of this function at each one of those points. And so I think I'm using, they're simple poles. Each one's a simple pole, so I can just use, I guess I could either think about it as using rule 1, or I could think about it as using rule 3. Anyway, the residues work out to 1, a half, and a half, and so you get 4 pi I. So that's kind of cool. So again, to recap, to calculate an integral, if the if we're talking about a simple bounded curve, we just have to locate the singularities, the isolated singularities of the integral of the function we're integrating, and use the residue theorem. That calculates the integral for us, right? Assuming that it's positively oriented and it's just covered once, right? If you had a curve which you wound around like 10 times, then you have to adjust your logic for that. All right. Now this one here, I say express this integral as a contour integral. Do not try to calculate the contour integral. All right. So I was too lazy to come up with an example that you could calculate for this test. I just set it up. So we make the substitution like we just talked about a few minutes ago. Plug it in, and lo and behold, this is equal to that. Yay! And of course, to actually calculate this, you could multiply by like z over z, get a quadratic in the denominator. Quadratics we can always factor and suffer through the calculation. Like, we could finish this. I must have been weak-willed this semester when I didn't make them finish that. Come on, man, they could finish that. Oh, this is why I didn't make them finish it, because I wanted them to do this. That's why. Oh, yes. Up to this point, you probably have the feeling like, this isn't that bad. These calculations are kind of easy. And they were. Until this problem. Actually, this problem's not too bad either. But here, we're supposed to calculate the limit as r goes to infinity of CR. Oh, this is kind of sneaky. So I've asked us to calculate the limit as r goes to infinity of the upper half circle. Now, we know that that's going to 0. I think it goes to 0. And then I said calculate and derive from the limit above the principal value of the integral of f of x dx for appropriate f of x. Oh, this is a very vaguely written question, but I like it. I guess I like it. Anyway, so what I do is I look at f of z as 1 over z minus I times z plus 2i. It's got simple poles at I and minus 2i. Okay, but I is up here, and down here is your minus 2i, right? So minus 2i doesn't matter. It's not an element in the interior. Now, oh, I'm using different notation. CR for me is the union. It was this is CR would be boundary of R in our previous discussion. So, excuse me, CR plus is actually the half circle, and LR is the diameter. And all right, so the Cauchy residue theorem says it's 2 pi I times residue at I, which happens to be 2 pi over 3 when we work it out for this one. But on the other hand, we can bound the modulus of the function using triangle inequality stuff. So we got modulus of z minus I, modulus of z plus 2i, and this is an important triangle inequality to know about. So if I have in the denominator, I can make this larger, right? I can make this right here, z modulus of z minus I. I can make that this right here, what I'm underlining over here, double underlining, is smaller than that, all right? And likewise, this is larger than that. So what have I done? I've made the denominator smaller, hence I've made the fraction larger. And then, of course, we're on the unit circle, not unit, but the radius r circle. Modulus of z is equal to r, and then I wait a minute, absolute. What happened to my absolute value? Absolute value of r minus 1, absolute value of r minus 2 is just r minus 1, r minus 2. Well, what am I doing? I'm assuming that r is greater than 1 and 2, which is probably reasonable since we're interested in the limit as r goes to infinity. And so, lo and behold, we have proved that the limit, by the ML theorem, and here the length of that is pi r. So pi r over that is a bound. ML theorem, as r goes to infinity, that goes to 0. And so what we find is the limit as r goes to infinity of L sub r is equal to 2 pi over 3 times, where's my 2 pi I? Dude, where's my 2 pi? Oh, the 2 pi I cancels. Okay, great. So it's 2 pi over 3. And, oh, yowzers. Whoa. Whoa, 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 what's going on here? Oh, then the question is, what is this actually telling us? So there I'm actually needing to calculate, what is this? Well, making it real, a little bit of calculation, we get x squared plus 2 minus ix over x squared plus 1 times x squared plus 4 is that, which actually tells me two different things. It tells me, on the one hand, that the integral over the real part is 2 pi over 3. It also tells me that the integral over the minus x over that is equal to 0. Of course, the fact that the integral over minus x over that is 0 is immediately clear from the fact that minus x over that is an odd function. The principal value of any odd function, 0, because you're integrating from minus r to r, so by usual integration theory, that's 0. Indicate two other types of contour integration which we considered in homework. Well, we haven't done that yet, so I mean, whatever, later. So there you go. That's like a old test that I gave in here. The other thing I wanted to point out, if I still have your attention, if I don't, well, I'm sorry, but so I'll probably do some more of these in class, depending on what you guys are interested in. These notes are posted on the website. I'll try to make a link in the announcement, I guess, again, but I talk about examples like 100 through 117 or something. I think examples 100 through 108 are actually like residue calculations, which we've kind of already done, but 109 through 117 are actually, decent integrals. I think we just talked about that one already. Some of these I've already converted into the notes. Let's see here. This one's kind of nefarious. Look at this here. Look at this thing. This one's got an interesting trick in it. It's got an interesting trick. I'm getting tired. I'm going to stop here in a second. But so let's see here. The usual substitution over the unit circle gives you this, right? But then it's unpleasant if you just do that integral. So I simplify it to this, which gives us that. Oh man, z to the 4th. Dang. So we get 4iz dz over z to the fourth minus 6z squared plus 1. And my wife said make a w equals z squared substitution back in the day. And I said, okay, why not? Let's do it. So if you make a w equals z squared substitution, then w equals z squared means dw is 2z dz. And z equals e to the I theta gives you z squared is e to the 2 I theta, which means that c gets covered twice in the w variable. See, I don't think you'll find this calculation in any complex analysis book. This is from physics. She had a course with a Russian who understood calculus more deeply than most mathematicians. But anyway, so if we make this w equals z squared substitution, you gotta be careful because it ends up in the new variable covering the circle twice. So, see that 2 there. So then you get 2I dw over w squared minus 6w plus 1, which then that factors, it's just quadratic, it factors, and then you got one singularity inside, one singularity outside, you calculate your residue, multiply by 2 pi I, and then another 2 since you're winding twice. Man, this example's cool. And yeah, so you get pi times root 2. But dang, like if you just tried to calculate that, see, this is, man, this is hard in the original because you got to factor this quartic. What are the zeros? I mean, I guess maybe it factors actually. Maybe if you just make a z, probably if you make a z squared, like a w substitution here. Yeah, okay, so if you can do this algebra, then you could go back and do it in z as well. But this is neat. It's something I don't think about much is, like, what about substitution for a complex integral? That may be the only example of a substitution for a complex integral that I have. All right. So this, I think, is a homework problem you guys have already done. We'll talk about principal values soon enough. I'll probably do some of these examples in class next week. Here is a different way to argue the bounding theorem that I think is from. Oh, from here's a different way to argue the bounding theorem from. Sorry, I'm flipping through things like this. Through Saff and Snyder. We still need to talk about fractional residues and all that jazz. What I wanted to point out in here is I mentioned, oh, this is actually, okay, so that's the examples. This was the examples 100 through, through 117. Then there's also an old Mission 8 solution, which I should mention briefly since otherwise I'm just going to forget. And this has got some partial fractions calculation that's kind of cool. In particular, this is posted on my website, by the way. So here's some Laurent calculations, residue calculations, more residue calculations. But this one here is cool. Like this is what I'll end with today. So I mentioned that if you understood the residues, you could use it to calculate partial fractions. I actually do that in this example. It's actually a mixture. So I'm trying to find the partial fractions here for, well, there's 2 examples actually. So first one is 1 over z squared minus z. That factors to z times z minus 1. So by the theory we went over last class, that's got to be the residue at 0 divided by z plus the residue at 1 divided by z minus 1. And since the residue is respectively minus 1 and 1, there it is. Now, of course, you can also just do the algebra here, of course. But now the next one, a little bit more interesting. Here you got z squared plus 1 squared, and so that would have the partial fractions decomposition like so. There's 4 terms. Now 2 of these are really easy to get because you can just plug in the 0, right? You multiply by the denominator, plug in the thing. Of course, this is only true in the limiting process, which I'm sure Dr. Sprano has told you if you've had his calculus, but if you haven't, oh well. And yeah, maybe other people do that too. I don't know, whatever. Anyway, so plugging in I, 0, a 0, a 0, you just got that one. So we get 2i squared, which is minus 4, so d is minus 1/4. Plug in minus I, well that's 0, that's 0, that 0, just leaves you this. Minus I squared again, it gives you minus 4 times b is 1, which b is minus 1/4. But annoyingly, you don't get anything about a or c. But the thing is, a and c are the coefficients for the reciprocal terms, which means that a is the residue of f at minus I, and c is the residue of f at I. So you can calculate the residues using like our rules. In particular, I think we use rule 2, it's a double pole. Let's use the double pole rule, and voila, I over 4 and minus I over 4. There's a common 1/4 to everything I factored out, and there's your partial fractions. That's pretty nice, because anytime you've got a double pole in your partial fractions, or worse, a triple pole, it's kind of a pain to find the coefficients. Like what I end up doing usually is I differentiate the equation and then evaluate it. But man, this is a much more, you know, this is a faster path to that. Anyway. So that, again, this is from, I'll try to put a link. This is from my old Mission 8. We already actually looked, this page we also looked at earlier in this lecture, video, whatever you want to call this thing. We looked at that as well. That's also from this Mission 8. So I guess I need to make an announcement. So, all right, anyway, I think that's a good start. We'll do more of these integrals next week. So have a good weekend. Thanks, guys.